Hello everyone, and welcome to today's learning session on good practices for assessing accuracy and estimating area of remotely sensed change maps, organized by World Wildlife Fund's Forest and Climate Initiative. Thanks for taking the time to join us. My name is Breen Burns, and I'm the Program Officer for Learning and Communications. My colleague Maria Jose Pacha, our knowledge sharing and learning manager, and I will be your facilitators today. Our presenter is Dr. Pontus Olofsson, Assistant Professor in the Department of Earth and Environment at Boston University. Next slide, please. Before we begin, I'd like to share a few housekeeping tips and reminders. Today's presentation is being recorded, and you can access the recording within a few days on our YouTube channel. To access the recording, simply go to youtube.com and search for WWF Forest and Climate Initiative, or go to panda.org/forestclimate and look for the red learning section. There are two audio options. You can listen via your computer speakers or dial in through the number that was provided in your registration email. It's important to remember that if you experience audio difficulties while listening via your computer speakers, this can be caused by having multiple software or internet applications open. So please feel free to close some of them, or you're always welcome to join via phone. Questions are absolutely welcome. Please type your questions into the question area in the GoToWebinar panel. Pontus will answer as many questions as time will allow during the Q&A portion of the webinar. If you're having any technical difficulties, please submit them to me via the chat area if possible. Thank you again for joining us, and with that, I will turn it over to Pontus to get us started. Thanks, Pontus.
Well, thank you very much, Breen, and thank you all for tuning in. It's great to have so many of you here. My name is Pontus Olofsson. As Breen said, I'm with the Department of Earth and Environment at Boston University. We used to be Geography and Environment, but we just changed our name to Earth and Environment. And today I will talk about good practices for designing and implementing an accuracy assessment, and how to use the results of that assessment, of the accuracy assessment, to further estimate area and accuracy, and also confidence interval of the area estimates. And before we start, I would like to mention that everything that I will be talking about are in these two papers here. The first paper is called Making Better Use of Accuracy Data in Change Studies, and that paper discussed the analysis part, so like the last step of the accuracy assessment, how to make use of the error matrix to estimate all this stuff. And this paper is published in Remote Sensing Environment, which is not an open source journal, so if you don't have subscription, you can't access this. But if you just send me an email, I'll have an author personal copy that I can provide you. And the second paper here is called Good Practices for Assessing Accuracy and Estimating Area of Land Change. And that paper encompasses all the different steps of the accuracy assessment and the area estimation. And that is not published yet. It's currently in review in Remote Sensing Environment. But again, I can provide you with a draft if you're interested. And I would also like to mention that all this stuff is funded by Silva Carbon. Silva Carbon is the U.S. contribution to the Forest Carbon Tracking Task for implementing RED and RED+. And none of this would exist without Silva Carbon. So I'm very grateful for that. So let's get started here. Let's start from the beginning. Why is this important? Why do we need to go through the exercise of estimating area, doing accuracy assessments, and all of that? Well, first of all, why do we want to use remote sensing? What is the strength of remote sensing in the first place? Well, the strength of remote sensing is that it provides wall-to-wall coverage of the area of interest, the area we want to study. Whether that area is a small study area or a country or a continent or even the globe, remote sensing can provide wall-to-wall coverage of the area, and that is very valuable. Because with that, we can make a map, and we can map the areas of interest, such as deforestation, directly. You simply count the pixels in our map and get a value or a number of the amount of forest harvested or any other change process. The weakness of that, though, is that the results are never perfect, at least not in reality. I mean, we're trying to capture pretty complex continuous processes by classifying pixels into a set of a few discrete classes. And that is typically hard to do, right? And the result of that is rarely perfect. Plus, we then might have issues with atmosphere. There might be issues with the training data if we're doing a supervised classification. There might be issues with misregistration. The georeferencing might not be perfect. There's a whole bunch of issues that will contribute to errors in our classified map. So it's fair to assume that any map you make will always have errors in one way or the other. And if the map has errors, then the areas of the different map classes have errors, and they're not correct. So what we need to do is to identify and quantify those errors. And then we need to adjust the areas of the map classes for those errors. And to quantify the uncertainty in the area estimates, we also need to provide a confidence interval of our area. And the beauty of this is that it's actually quite easy. It's really not that hard. Once we have our error matrix, it's a few simple calculations that I will show you how to do. And I would also like to mention that this is not new stuff. This is not new research that me and my colleagues have figured out. You know, we're leaning heavily here on a book from 1977, Cochrane's book, Sampling Techniques. The third edition was published in 1977. So this is pretty old stuff. This is nothing new. And there is a paper from '82 where a guy at NASA Ames called Don Card, he made use of these techniques in one of his mapping studies. So this has been around for a long time. This is nothing new. But I think in order to understand these techniques, we need to introduce some terminology. And for you who have some experience doing accuracy assessment and stuff, you're aware of this, but this is very important. So let's start from the beginning here. So as I say, we need to identify the areas in our map in order to adjust for them. And we do that by designing and implementing an accuracy assessment. And the whole idea behind the assessment is that we treat our map as the population. And from that population, we draw a sample. And then we examine each sample unit in that sample. We step through the sample unit in our sample, and we provide a reference class label. So if we have a 3-class map, then we step through each of the sample units and provide one of those 3 labels on it. And the reference, we call that the reference classification. So once we have labeled all of the sample units, we have created a reference classification. And the whole idea is that the reference classification is of higher quality than the map classification, right? Or, you know, as close as possible to represent true conditions on the ground. So we have our map, our image classification, and then we have our reference classification. And by comparing the two at each sample unit, we can construct the error matrix. And we have an error matrix on the bottom of this slide here. This is an error matrix for 3-class change map, where class 1 is deforestation, class 2 and 3 are stable forest and stable non-forest. And the map here is represented by the rows. So the map classes are represented by the 3 rows. We have them here. So for example, we have a total of 500 sample units. You can see that here. And we allocate 100 of those to map class number 1. Map class number 1 being deforestation. And then the reference data is represented by the columns. So in this case, out of the 100 samples allocated to the deforestation class, 97 of those turned out to actually be deforestation when we looked at those sample units in our reference classification. So the diagonal here represents the number of correctly classified sample units, correctly classified according to our reference classification. And off the diagonal we have the errors. And there are 2 types of errors. So again, for class number 1 we have errors of commission. So errors of commission are sample units that were classified as deforestation, but when we looked in the reference data, they turned out to be stable land covers. In this case, there were 3 sample units out of 100 that were classified as deforestation but turned out to be stable non-forest. So these are the errors of commission. They indicate an overestimation of the class in question, right? So we have a lot of these as an indication that this value here, the map area of class 1, is overestimated. Now, in addition to errors of commission, we also have errors of omission, and that's these guys here for class number 1. So these errors are sample units that were classified as stable land covers, but when we looked at these sample units in our reference data, they turned out to be deforestation. So there were 3 sample units here that were classified as stable forest, but in reality they were deforestation. And there was another 2 sample units that were classified as stable non-forest that turned out to be deforestation. So we have a total of 5 errors of omission for class number 1. And if we have a lot of these, it's an indication that this area is underestimated, because this is omitted change. That's why we call them errors of omission, right? They were classified as something else, but they turned out to be deforestation. So it's deforestation that was omitted or missed by our change map. So what we need to do is to, let's assume we have a map, and now we need to get to that error matrix. And once we have it, we need to make use of the data in that error matrix to calculate accuracy area and confidence interval. So how to do this? And I think the best way to explain this is with an example. And I'm going to use an example from the literature here. I'm going to make use of a map that was made in New England, or for New England, a change map that mapped conversion of forest to urban and rural development, urban and commercial development, and then farmland abandonment, and then stable forest, stable non-forest. And this was done by Sung Bae, one of our grad students here at BU. She published this year in Journal of Land Use Science. So before we start, the first step of this whole process is to design our sample. So I said that we treat our map as the population. So the first thing we got to do is to draw a sample from that map. And we need to design the sample. And that refers to the sampling design. And there's a couple of ways to draw that sample. You know, we have a map here. This is obviously not New England. This is Africa. But if we could, for example, draw the sample completely randomly. So all the pixels in our map, we have those, and we just pick a certain number completely randomly. And we might end up with something like this. So a completely simple random sample. As an alternative, we can do a systematic sample, where each of the sample units are at a fixed distance from each other. And this is good if we want to visit these sites in the field, for example. You know, it's going to be easier to find these than to find these, for example, right? Because they're at a fixed distance from each other. As an alternative, we can stratify our sample. So we make use of the information in the map to create strata. And then we can put as many sample units as we want into the different strata. And that might look something like this. So in this case, we have kind of our desert strata, you know, the Sahara Desert, and also here, that is undersampled. So we put relatively few samples in the desert because we're not particularly interested in that. But then we got the red stuff here and also the green stuff here along the coast that we're more interested in. So we put more sample units into those strata. And the stratified design has some very obvious advantages because it allows us to target rare map classes. You know, we can define our strata as the different map classes, and then we can put as many samples as we want into those different strata. And that is when we're working with change maps, we typically have change categories that are just a fraction of the total map area. So the stratified random design allows us to target those small map classes. So in this case, we have our map of New England, and we have three classes. We have deforestation, stable forest, stable non-forest. This is like one part of the New England map where there was no farmland abandonment. So we only have three classes. And the deforestation class occupy about 1% of the map. And the stable land covers occupy 99% of the map. So if we don't stratify, let's say we draw a simple random sample of 500 sample units. The estimated number or the expected number of sample units in the deforestation class would be only 5. And there's not much we can do with just 5 samples. But the stratified random sampling design allows us to put as many sample units as we want into the deforestation class. So let's stick to the stratified random sampling design for that reason. The second step is to determine the total sample size. So we have our map. We're going to draw a sample of a certain number of sample units from our map, but how many sample units? Right. Are we going to do 50? Or are we going to do 100? Are we going to do 10,000? Are we going to do 50,000? And there are a couple of ways of doing that. We can either just settle for a number that we feel is manageable and we can afford. I have time to do 300, and I have money to only do 300, so I'm not going to do more than 300. That's fine. We can do that. A better option is to actually use the variance formula for our sampling design, in this case stratified random sampling. If we assume certain levels of accuracy, we can solve this formula for n, and then we get an estimate of the sample size. So once we have our total sample size, we need to figure out how to allocate those to the different strata. So as I said, we have 3 map classes. We will define our strata according to those map classes. So how many sample units are we going to put into the different strata? I mean, if we have, let's say we have 1,000 samples, we could just simply split those 1,000 in 3 and put a third in each of the map classes, or in each of the 3 strata. That's one way of doing it. And there are other ways of doing it too, and it really depends on the objective of your accuracy assessment. If you're interested in user's accuracy, you know, class-specific accuracy, then just splitting them by the number of strata, that's fine, you can do that. In this case, we're also interested in area. We want to do an area estimation here. So we have kind of competing objectives. We want to estimate both accuracy and area. So what we recommend in a good practices document is to put 100 sample units per change class, and then we split the difference among the larger classes based on area proportion. So for example, in this case, the researcher who did the study should settle for a total sample size of 500 sample units. So good practice would then stipulate that we put 100 of those units into the deforestation class. And then the remaining 400 would be put in the stable classes, such that 64% of those 400, right, 64% stable forest, 64% of those 400 will be allocated to the stable forest stratum, and 35% of those 400 would be allocated to stable non-forest stratum. So that would give us 100 sample units in the deforestation class, 260 in the stable forest class, and 140 in the stable non-forest class. Now what she did is that she put 100 in the deforestation class, and then she put 300 in the stable forest class and 100 in the stable non-forest class. So pretty close to our recommendations. But she did this way before we wrote up this, so she couldn't make use of that document at the time. But she was very close to following these guidelines here. All right, so now we have a sampling design. Right? We have settled for a stratified random sampling design. We have estimated a total sample size. In this case, we settled for 500 sample units. And we have allocated those 500 to the 3 different strata, 100, 300, 100. The second step here is to step through each one of those 500 sample units and provide a label that is either deforestation, stable forest, or stable non-forest. And this whole process of reaching an agreement between the reference data and our map is what we call response design. And in this case, we're going to make it simple. We're going to just treat our sample units as pixels. Right? Our map is made up of pixels, and our sample units are pixels too. Let's keep it simple. What we need to do is to find a source of reference data. This is a very important part of the response design. So when we step through our sample units, we need data to determine what is the land cover for these different sample units. And the data we use to make that call is called reference data. And preferably, the data we use for doing that, the reference data, should be of higher quality than the data we use to make our maps. But we can also use the same kind of data as we did for making the maps, that we used when we made our maps. But then the process, and this is important, the process of creating the reference classification has to be more accurate than the map making process. So in this case, we used a supervised classification approach. So we had our Landsat data, we had training data of the different map classes, and we fed that to a classifier, and out came our maps. The process of creating a reference classification, if we also want to use Landsat data for our reference data, that the process of creating those or providing those labels has to be more accurate than the process of supervised classification. And I would argue that if we do a manual interpretation of each one of these sample units by looking in our Landsat data, that is a more accurate process than just doing a supervised classification. And now Landsat data is free, so we can download as much Landsat data as we want to determine what the land cover is for each of these sample units. And we can also use Google Earth. Right? We can use multiple sources of reference data. The more data we have, the better we will be able to tell what the land cover is for these different sample units. So in this case, we're going to use a combination of Landsat data and Google Earth to provide labels on the sample units, or for the sample units. And remember that we also use Landsat data to make our map. And that is perfectly fine, but the process then of creating the reference classification has to be more accurate than simply than the supervised classification process. So we do that. We identify, we use Landsat data and Google Earth, and then we step through each of these 500 sample units, and we have 3 hard-working interpreters that independently provide a label for each one of these units. So these 3 interpreters, they step through each of these sample units. They look in Landsat, they look in Google Earth, and they provide a label for these sample units. And once we have that, maybe I should also say that, well, I said it in the beginning, but it's worth repeating. The sample units, the labeled sample units, are referred to as our reference classification. So once we have stepped through all of our sample units and provided a label for them, we have created our reference classification. So once we have that, we can compare it to our map and make an error matrix. And that brings us to the final step of the accuracy assessment, the analysis. So the analysis specifies the procedures to estimate accuracy in area and confidence interval from the error matrix. So as I said before, we have our error matrix. We have compared the map and the reference classification for each of these 500 sample units. And we have our error matrix here expressed as sample counts. So again, we have 100 samples in class number 1, which is deforestation, 300 samples in the stable forest class, and then 100 samples in the stable non-forest class. And out of these 197 were correctly classified. There are 3 errors of commission and 5 errors of omission in our deforestation class. Now, if you look at the map areas here, you see that the amount of deforestation is 22,000 hectares. Stable forest is over 1 million, and stable non-forest is 600,000, right? So the area proportion is 1.3%, 64%, and 35%. So what we have done when we stratified our sample is that we put 100 out of 500, so 20% of all the sample units were allocated to 1.3% of the map. Another 20% of the sample units were allocated to 35% of the map. So the number of sample units in the different classes is completely unproportional to the areas of these different map classes. Therefore, we can't really use the sample counts to calculate accuracy and area, because the number of sample units is not proportional to the error proportion. So the first thing we got to do is to express our error matrix as estimated area proportion instead of sample counts. And that is very easily done. All we need is we start here with element 1. We take the area proportion for map class I. I are the rows, so we have I equals 1, I equals 2, I equals 3, and J are the columns, right, the reference data. So WI for class number 1 is 1.3%, right, this guy here. And then for the first element, Nij, N11, it's 97. And then we have Ni dot here, which means the number of samples for map class I, in this case 1. The dot means that we sum across the J's. We sum across the columns here. That would be 100. So it's simply 1.3% multiplied by 97 divided by 100. And then we do that for each of the elements in our error matrix. So here it would be 3 divided by 300 times 0.64. Right? Here it would be 279 divided by 300 times 64. It's a relatively easy calculation. So we do that, and now we end up with our error matrix expressed not as sample counts, but as area proportions. And this is much more informative than just looking at the sample counts. Because now the error matrix is expressed in area, or estimated area proportion. So instead of saying that we have 97 samples that were correctly classified as deforestation, we can now say that 1.2% of the map was correctly classified as deforestation. Right? And the errors of omission and the errors of commission are not expressed as 3, 2, and 1, and so on and so forth. They're now expressed as a percentage of the total map area. And this is very helpful, and this is very useful, because if we now check, if we sum across the columns here, right, we sum for each row, we're going to get the area proportion according to the map. Right? So if we sum across the column for one map class, we're going to get the area proportion of this map class according to the map. And this should be identical to this guy here. Right? Now, if we sum across the columns, we're going to get the area proportion of this class, not according to the map, but according to our reference data. So if we do that for map class number 1, we see that we end up with 2.6%. So if we take this number and we multiply it by the total map area, we end up with an area estimate according to the reference data. And this is the error-adjusted area estimate. And it's error-adjusted because we exclude the error of commission. You know, the stuff that was misclassified as deforestation but actually turned out to be something else. But then we include the errors of omission. So the deforestation that we omitted in our map, we now include. So therefore we can call this an error-adjusted area estimate of deforestation. And we see that this is twice as big as the map area. And it's twice as big because we have a whole lot of error, a whole lot of omission error here. When we just look at the sample count, it said that we have 3 errors of omission here and then 2 here. It doesn't tell you very much, but when we look at the estimated error proportion, we see that this is actually a pretty substantial part of the map, 0.6 and 0.7%. And the reason for that is that these errors belong to classes that are very, very big. So these omission errors, the 3 plus 2 omission errors, they carried a whole lot of area weight and represents about 1.3% of the whole map. Right? That is why the error-adjusted area of deforestation is much larger than the map area, because the map omitted a lot of deforestation. So now we have area-adjusted area estimates of deforestation, where we just take this number and multiply by this number, and multiply by this number to get the area-adjusted areas of the stable land covers too. The second step is to calculate a confidence interval for these 46,000 hectares. calculate a confidence interval for the area-adjusted area estimate of the different map classes, starting with deforestation. And we do this using this equation here. And this might look a bit messy, but it's actually quite simple. All of the variables are in our error matrix. In this case, it's expressed in terms of sample counts, n, and as the area proportions. So we have our mapped area proportions, and then we have the sample counts for column 1. That will give us a standard error of the column total for class number 1. If we multiply this standard error by the total map area, we get a standard error of the deforestation of 11,000 hectares. And if we multiply the standard error by 1.96, or 2, rounded to 2, we get a 95% confidence interval of the area estimate. And if we do that, we end up with a final area estimate of the deforestation class, or of deforestation, of 45,600, around 46,000 hectares plus minus 22,000 hectares. And this is obviously a much more informative answer than, simply saying that the amount of deforestation is 22,000 hectares, right? Because this area is associated with errors of commission and error of omission. This area estimate is adjusted for those errors, and we have also estimated a confidence interval so we can express the uncertainty of that area estimate. And as you can see, it's actually quite high. There is a relatively high level of uncertainty associated with this area estimate. And then we can redo these calculations for the other two classes too. And finally, what we want to do is to calculate accuracy. So far, up until this point, we have estimated area and confidence intervals of those area estimates. The last step is to calculate or estimate the overall accuracy, the producer's accuracy and the user's accuracy. And again, everything is in the error matrix here. The overall accuracy is simply the diagonal summed. So the amount of correctly classified deforestation, stable forest, and stable non-forest. And in this case, the overall accuracy is 94%. The overall accuracy for class number 1 is 1.2% divided by the row total, which is 1.3%. So the user's accuracy of the deforestation class is very high, 97%. The reason for why that is high is that we have very little errors of commission. So the user's accuracy is indicative of errors of commission. And we have very little of that here. And finally, we have the producer's accuracy. So for class number 1, it's again the amount of correctly classified deforestation divided by the column total. And in this case, it's 0.48. So the producer's accuracy is just 48%. And again, that's because we have a lot of errors of omission here. So the producer's accuracy is indicative of the level of omission error. And since we have a lot of omission error in our map, the producer's accuracy is very low. And I think I have a few more minutes maybe. And I just want to show, I had these nice animations here. So, this is theory. That's what we should be doing, right? We should estimate area. We should estimate confidence intervals. You shouldn't publish any areas estimated from remote sensing without having adjusted for errors and calculated a confidence interval. But is this really being done? And to find out, we screened two of the main remote sensing journals, Remote Sensing Environment and International Journal of Remote Sensing. We looked at all the change studies published between 2005 and 2010, and we kind of categorized them according to the level of accuracy assessment. And we found out that a lot of these papers, they don't really go through this exercise. There is very few papers that even publish the information required to calculate confidence interval in adjusted area. And out of 57 papers, only 3 papers published a change area that had been adjusted for classification errors. And more than half of these studies, they didn't even assess the accuracy of the change map itself. A lot of these studies are post-classification comparisons where you have 2 maps at 2 different times, and then you overlay them. And instead of assessing the accuracy of the final change map, the accuracy of the individual land cover maps were assessed. But that doesn't tell you too much about your ability to map change. And this is something we're trying to change. That is why we write these papers, and that is why we write the good practice document, is to show that these calculations aren't that hard. And if you've gone through the trouble of making an accuracy assessment and you have your error matrix, it's actually quite straightforward to estimate area and confidence interval of your area estimates. And I think I'll stop there. I think that was 45 minutes. So I'll stop there, and thank you very much for listening.
Okay, well, thank you, Pontus, for this very interesting presentation. I think that you presented the topic in a very easy and interesting way. So we have a few minutes for questions here. So we have here we have Lloyd Gamble. He has a question. Can you talk more about creating the reference data? In example, you used Landsat and Google Earth, but how does error in reference data get accounted for? And I am going to give the floor to Lloyd as well if he wants to say something else about that. Yeah.
Maria, I don't have any further clarification. I was just curious how any potential errors in that reference data would percolate in the overall error analysis.
Yeah, that's a really good question. And if you have errors in your reference data, that is obviously a big issue. And the papers that I have written, the good practice document, doesn't really talk too much about that issue. But one of my co-authors on both of these papers is Giles Foodie, and he has written a couple of papers focusing on just this issue. And I'm going to have to refer you to those papers. So if you search the literature for Giles Foodie, you'll find a couple of papers discussing this issue. There is also Gil Pontius at Clark University who has investigated the issue of having errors in your reference data. But the bottom line is that that is serious. If you introduce errors in your reference classification, that will have an impact on your final result, and that should be accounted for. But the good practice document and what we are doing so far, we haven't really dealt with that. We just assume that the reference classification is correct. But it's an important issue that needs attention.
Thank you.
Okay, well, thank you, Lloyd. Something for everybody to be aware of is that these questions and answers will be posted in redcommunity.org in the section on conversations, because we have a lot of questions and I'm not sure whether we will be able to answer them all. So the other question, the second, is by Miguel Munoz, and he asks, if I decided to use blocks like a way for performing my validation, how can I determine the amount for stratum? And what is the way for sampling in blocks, pixels, clusters of pixels? So I will give the floor to Miguel if he wants to clarify this question. Hi, Miguel.
Hi.
So do you want to add anything else to this question to Pontus, or it was clear enough?
Yeah, this is my question for Pontus. How many blocks can I put in Stratum?
So in this case, we just assume that each sample unit is a pixel, but there is nothing that prevents the sample unit or the spatial assessment unit, as we call it, for being something else. And if you're using blocks, it will change the analysis slightly, but it's still valid. And if you're talking about clusters, if you have a cluster sampling, then you would have to use a different set of equations. In this case, I'm using a stratified random, a stratified random sample. And the equations I showed are for the stratified random design. If you're using a cluster design, it will complicate the analysis a bit. And we actually don't recommend cluster design unless it's absolutely necessary. If it is necessary, then one should use the cluster design. And there are ways of calculating accuracy and area estimates and confidence interval and all of that using in a cluster design too. Those equations are not in the papers that I mentioned.
Okay.
And the blocks is so in a block you would assume that, so the block is different from a cluster, right? So in the block you would use many pixels as your sample assessment unit.
Yeah.
Yeah. Well, then that's perfectly doable too.
Okay,
And
thank you. Oh, sorry.
I just want to mention we have two papers in International Journal of Remote Sensing that we'll be happy to provide you, where we have done accuracy assessment and sampling designs using a block sampling approach.
Okay. Thank you.
I'll be happy to provide you with those papers.
Okay. Thank you, Pontus.
Okay, thank you, Miguel. We have another question by Hamad, and he says that on slide number 11, 100 samples were used for deforestation, but how we can know exactly from reference data deforested pixels?
So we have our map, right? Okay. Should I wait for the question, maybe?
The question is there. I gave the floor to Hamad just in case.
Okay, sorry.
Hello, Hamad.
Hello.
Hello.
This is Hamad. Actually, I am working in Nepal and especially looking the deforestation. And when we are looking at deforestation, how I can exactly know from my reference data, then I will compare the two images, then I can know the deforested pixel, instead of only using the reference data and saying these are the deforested pixels. So this is how you use 200 samples. This is I would like to know.
Well, preferably when you look at the sample units. So first of all, when you do your accuracy assessment, you would have your 500 sample units. You would allocate them to the map, right? To the different strata. And then you would go through each of those 500 sites, but you wouldn't know which sample units are in which strata.
Mm-hmm.
And preferably, by looking in your reference data, you would be able to make that call. Right? If your reference data is of high quality, you should be, hopefully you would be able to determine if the sample unit has experienced deforestation or not. And if you're using Landsat data, for example, you might want to use a whole bunch of Landsat images to make that call. And in the example I provided, we used a combination of Landsat data and Google Earth to make that call. And to make things easier, we would also then preferably have 3 interpreters that that would look at each of these sample units. And then you can hopefully break a tie to make a decision on what has happened for that sample or in that sample unit. And then there are more complex methods too, where you can do like a fuzzy classification approach, where you can provide, you know, instead of saying that this is deforestation or not, you can have like a sliding scale, and there's different ways of doing that. That would complicate the analysis a little bit, but it's perfectly doable, and there's a lot of papers showing how to do that too.
Mm-hmm.
But in the ideal world, you will look in your reference data and be able to make that call. And if you absolutely can't do it, if there's no way of telling what has happened in this sample unit, you could throw it away.
No, okay.
If you absolutely can't
another
say
thing
anything.
is related to this. Another thing is what you prefer. One analyst should do classification and the other should do for accuracy assessment, or same person can do accuracy assessment. Normally the same person if do an accuracy assessment and he like biasing, he do biasing by himself or herself to saying that this is correctly classified.
Yeah.
So this case, what you prefer? Another analyst should do accuracy assessment for you, your classified data?
Well, I think what is important is to use more than one, because usually what happens is that if you have 1,000 sample units to label, it's a very high probability that you will make a clerical error. You know, you would say that this is deforestation, so you put down a 1, but you accidentally put down a 2, for example. Or you put the wrong label for the wrong pixel. That's very common. So if you have 3 interpreters, you minimize the risk of that happening, or you can at least find those errors. So I think that is very important, to have at least more than one doing it. Whether it's the image analyst or not, that's I think preferably you would use somebody independent. When we do these kind of things here at the university, because of lack of resources, we always have the image interpreter being part of the interpretation of sample units. But the important thing is that he doesn't do it alone. I think that is the take-home message. That regardless who is doing it, if it's the image analysis or not, have more than one person look at the sample units.
Okay, well, thank you, Hamad, and thank you, Pontus, for answering that. We have a question from Naikoa Aguilera Muchastegui. He wants to say, question on maps made with different sources of data and stratification. And I'm give the floor to Naikoa to clarify this better. The floor is yours, Naikoa. Naikoa?
Hello, yes, Pontus, this is a question that raises up from the reality that MRV practitioners in countries are now facing, which is the fact that due to limitations that optical data such as maps that presents with problems such as cloud cover and shadows and things like that, they're actually having to come up with maps that combine radar imagery and optical data from different sources. And then at the end they produce an overall map. So how do you suggest dealing with this accuracy assessment? Do you think that they can go ahead and do the accuracy for the overall output map independent of the sources? Or you suggest that they should stratify, incorporate the source data they use to assign the condition of each pixel into the stratification for the random sampling for the reference data?
No, I think that you should treat the map as a whole. And you shouldn't care too much which data that was used to make the map. At the end of the day, you have a map with a set of discrete classes. And that is the map that you want to assess, regardless of which data you use to make the map.
Well,
so
those are great news because that will save folks a lot of work.
Yeah, I would treat the map, and preferably, in an ideal world, there wouldn't be any difference between areas of that map classified using one data source or the other. And I would treat the whole map as the population and then draw a sample from that population and stratify by map class rather than by input source data. But again, the response design require you to create a reference classification requires a process that is more accurate than making the map.
Yes.
So if there's different methods that were employed in making a map, you have to make sure that the process of creating a reference classification is more accurate than the processes made to make the map.
Yeah.
But
yeah,
I wouldn't stratify based on input data.
Awesome, excellent. One thing that I could perhaps complement on the reference data is that for folks to keep in mind is, well, the ideal would be field work and field, validation, ground truthing.
Yeah.
Especially incorporating a little bit of the history of the location that you're talking about, because condition versus actually what's going on, because we have a lot of sources of error, for example, with itinerant agriculture.
Yeah.
And things like that. But then you have higher spatial accuracy imagery and even phenological data. So for folks to keep that in mind, that's the kind of stuff that you can use. Thanks.
Yeah. Thank you.
Okay, well, thank you. We have the last question by Miguel Fernandez. He says, very useful talk. I have one question. What happens if you do ground truthing for reference data, but you cannot access these areas? How do you do the sample design?
Yeah, accessibility.
Yeah. So if we are trying to assess a change map, it becomes a bit tricky to use field data. I mean, if we have a change map that represents changes over 20 years, it's hard to go out in the forest and look at that site and assess what happened, what is the historical land use of this particular site. So in general, field visits might not always be motivated if you're trying to assess the accuracy of a change map. Now, if that is the only option and there are certain areas you can't access, then we would say that the inclusion probability of those areas would be 0. And if the inclusion probability is 0 for a certain part of the map, then that is not good, and it kind of violates the probability sampling. If it's a very small area, then it might not be such a big issue, but if it's a larger area, then it will be complicated. One solution would be to kind of mask that out and just not include it in the estimation process. So you would estimate area for the areas where you can actually visit. But an alternative would be to maybe use a combination of different reference sources. So if there are places that you can't visit, maybe you have another source of data you can rely on, such as aerial photography or high-res satellite imagery or even Landsat.
Okay, well, thank you. Well, we are almost 1 minute away from finishing this. And Pontus, I would appreciate if you can put the last slide.
This one?
No, the last slide of the presentation.
Oh.
Not your one.
This one?
It's the one a little bit.
This one.
Yeah, that one, great. So, Bryn, can you mention what are our resources?
Yes. So if you'd like to learn more, if you'd like to watch the archive of this or other learning sessions, you can go to this web address. You can also go to panda.org/forestclimate and look for the red learning session, and you'll find many more learning tools and resources. You can also sign up for our RED Resource Digest, which is a free weekly roundup of RED news and information, or Canopy, which is our quarterly e-newsletter. It's also free and covers RED news and information. So thank you again for joining us. And Pontus, if you could go just to the next slide. There are a few more resources. So you can also keep up with us on Twitter. You can visit the website again. There's the URL, our email address is there, and as Maria sent to you all and mentioned, you can also find information about this webinar and the follow-up and additional questions that we didn't get a chance to answer with Pontus at redcommunity.org in the conversation section. We will post that in the next few days. So next slide, please. In closing, we just want to say thank you. And we hope you found this webinar useful, and we will see you at the next one. Thank you to Pontus, and thanks to everyone for joining.
Well, thank you.
Thank you. Thank
Bye.
you all.
Bye.